Hello, my name is Achintya Haldar. I am from University of Arizona. I'll be talking to you today, computing innovation in the reliability analysis of nonlinear dynamic systems in the metaverse era. We call this method as REDSET. I have been working in this area for over 4 decades. I am going to talk to you the most recent work in this area as of today. The outline of my talk would be that discuss the metaverse. Then my presentation has several mathematical elements. Due to time limitation, it will not be possible to discuss mathematics in detail, but information on references will be provided at the end of this presentation. And I'll try to identify some of the computing innovation in the current work as I move forward. Now, metaverse, I call it fourth era of computing and networking. The first era was main computer between 1950s and 1970s. Second era was personal computer and internet between 1980s and 2000. Currently, we use mobile and cloud, and the next era, I call it fourth era, would be computing era. Now, metaverse, if you talk to some of the experts, they will call it a dynamic internet, and it would generate about $13 trillion per year in 2023. In design, when I was a student, I used allowable stress design method. Then ultimate strength design method was introduced. To consider uncertainty in the load and resistance variable, we used LRFD, load and resistance factor design. And then, at least in the US, we are talking about performance-based design, PBSD. PBSD is a very sophisticated risk-based concept. However, when it was developed, they did not identify which program or which concept should be used for the reliability evaluation technique. It is basically, there are different performance level. What happened during an earthquake, people know in the past we used called life safety events, but now we observe there are a lot of economic consequences of earthquake, and to absorb that economic consequences, we call it performance-based design. They call it collapse prevention, life safety, and immediate occupancy. And you can see they are giving you the allowable drift values to take the risk. Basically, in performance-based design, owner or user can define or accept what risk they are willing to take and then mitigate it by buying some additional insurance. Risk is always estimated with respect to a performance function. In this figure, conceptually, I am showing you what is the limit state. Above the line, it is unsafe region. Below the line, it is called safe region. And the reliability index beta would be the distance between the limit state function and the origin in the reduced variable space. Now, if that function is readily available, we call it explicit limit state function. Means that function can be defined in terms of all the random variables present in the formulation. We can use then first order reliability method to estimate risk, or second order, or Monte Carlo simulation. What happened in 2000, I proposed stochastic finite element method. I realized most of the time, in most discipline, people use finite element, but all the variables are uncertain or unpredictable. And to consider that, I developed this method. Now the editor was John Wiley. They asked me to develop a mid-easy book because the stochastic finite element was too complicated. And this red book is the mid-easy book. It is now being used all over the world as a as a textbook. Now, for the problem we are now talking about, stochastic finite element method cannot be used. In the metaverse area, our limit state function is not explicit, but implicit in nature. And obviously, Monte Carlo simulation can be used for implicit limit state function, but I'll show you it cannot be done. Now, we can use the finite element method I developed earlier, but it is based on stress-based finite element. Most of you do not know what it is. You use displacement-based finite element method. It is little bit difficult and complicated. And there is no computer program currently available in the market that you can use. And it may not be able to consider highly nonlinear problem and that excitation applied in time domain. So for that particular reason, really, we need to find an alternative to the stochastic finite element method I developed earlier. Now, to consider uncertainty, also in the dynamic loading in time history, we have to use multiple time histories satisfying the design response spectrum. Now, I'm going to talk about three different types of dynamic loading today. First one is earthquake, extremely irregular. Wind-induced wave, it is moderately irregular, and thermomechanical loading, heating and cooling of computer chips. It is very different type of loading, but in metaverse area, we need to know how to do that. And obviously, we have to use multiple time histories to calculate the underlying risk. Most of you have seen earthquake loading. Here I am showing it, time domain of a typical earthquake for first 15 seconds. It could be 30 seconds. You'll find that during an earthquake excitation, some of the building is extremely damaged and the building next to it did not suffer any damage. What happened? The frequencies of the excitation and the frequency of the building, when it matches, it causes resonance condition. And sometimes when it causes resonance condition, you have failure. Sometimes when you don't have resonance condition, you have no failure. For offshore structures is little bit complicated because here I'm showing it how the offshore wave, wind wave, it acts on the particular structure, and you can see modeling that wave loading can be mathematically extremely challenging. Now, what we did, we developed a computer model for generating three-dimensional wave. I am showing it. It is an extremely complicated process. One slide may consist of about 150 megabyte of data. So what we did, we take that data, we took a slice, and then we can generate the corresponding time history of the wave. This is our very innovative concept really we proposed. Now for wave loading, there is another issue that we need to worry about, that wave loading changes with the depth of the water. At the splash zone at the mean sea level, though it is very, we see that really, but when you go down below the water, the force attenuate, and here it is known as Wheeler stretching effect. We consider that also in our model. So for wave loading, we can use the time history, and we use called constraint new wave theory, and we can generate multiple time histories for wave loading also. And then we can apply that wave loading to an offshore structures, and we can calculate the underlying risk. For solder ball, it is heating and cooling of computer chips, and you can see it takes time to build up the heat, then it remains constant, then it drops, and obviously we have to consider that for that particular loading. Now, risk is we have to consider uncertainty for both resistance-related variable and dynamic loading. I give you some brief idea about dynamic loading. Resistance-related variable, the area is well defined. The two books I talked about in the past, that can be used, or you can use that book to find out the how to quantify uncertainty in the resistance-related variable. Now, why do you need REDSET, that new method we are proposing? Because there is no method currently available. Some of the methods that are available, I am summarizing it: high dimensional model representation, support vector machines, artificial neural network, various space reduction techniques, sequential sampling, but most of them cannot be applied in time domain, cannot consider explicitly major sources of nonlinearity for large system. Now, in our method, in our idea, we feel the ideal thing would be, since my method, stochastic finite element method, the program is not widely available, if an user can use any computer program available capable of doing nonlinear finite element analysis, where excitation can be applied in time domain, and you'll find it will provide an alternative to the random vibration approach. And I'll show you simulation cannot be used for this class of problem. The other other point you need to consider is risk-based concept is non-starter for deterministic community. Your boss or my boss, they never heard of risk. So we need to make sure whatever we do, they also agree to it, because they make the final decision. So the new concept we are going to propose should be acceptable to both the deterministic and reliability communities. And that is the reason we need to have numerous computing innovations to develop the method. So what we are going to do, why simulation is not possible, I am giving you a very good example. For nonlinear time domain analysis of a small structure excited by earthquake loading, it may take about 10 minutes. If you want to simulate 1 million times, it would take 20 years or 19 years of continuous running of a computer. And obviously, we need to find an alternative to the simulation method. One option we thought that if we can generate even approximately the explicit response surface implicitly, implicit response surface explicitly, then we can use form first order reliability method to calculate or extract the reliability information. The RSM concept is a set of statistical techniques assembled to find the best value of the responses considering the uncertainty in the design variable. However, it was developed for biology and agricultural application. They did not use the complete statistical information of random variable. Also, we need to generate the response surface in the failure region for structural reliability evaluation. That means basic response surface method must be developed that would integrate that would eliminate all the deficiencies of the original response surface method. Now, to show what it is, what is going on here, these black dots are our sampling point, and it is generating a response using the finite element method, any method you are going to use, and we need to fit a polynomial through that responses. Once I do that, then we can use the shortest distance. We can use form to find out the corresponding reliability. As I said before, that we are going to integrate the form and response surface method. The reason is form iteratively locate the failure point. So initially, we are going to take the checking point values, is the mean values of random variable, and we'll fit a polynomial through it. Then using form, we are going to get the second coordinate of the checking point or the next coordinate of the checking point. We'll calculate the response and we'll get the another polynomial for it. Now, to fit a polynomial, what are the unknowns? Degrees of polynomial. How do you select that experimental design point where you need to calculate the structural response? Now, polynomial linear is not possible. We need to keep the degree of polynomial as low as possible. So we consider second order polynomial. There are two alternatives: second order polynomial without cross term and with cross term. And to define them, this coefficient B1, B0, BII, they need to be estimated. And to estimate those parameters is a very big challenge, and it depends on your efficiency of the algorithm. Two currently available method used for this purpose is called saturated design. It is relatively simple, but it is not that accurate. It can be used for both polynomial, second order polynomial without cross term or with cross term. The more advanced or accurate technique is called central composite design. It is only possible for second order polynomial with cross term, but it is very, very difficult. And here we are just trying to show what I'm talking about. These are the three. It is second order polynomial without cross term, with cross term, and CCD, and number of coefficient that we are going to use that indicates the number of deterministic finite element analysis you have to conduct. But when I use CCD, it will be 2 to the power k, and that is going to show up here. If k is large, k35 is not a large quantity, but if you calculate how many times you have to do deterministic evaluation, it could be of the order of 10 to the power 10, obviously not possible. So in developing REDSET, what we did, we were going to do first iteration and the intermediate iteration using SD without cross term. Once we locate the failure region, we are going to use CCD to calculate the risk accurately, but you can say that we cannot implement CCD. And for that, we develop very different, many numerous sampling design technique, innovative design technique. I do not have time to talk them here, but I'll give a reference for that in the future. Before moving forward, in CCD, what would they do? They use called regression analysis. Regression analysis is only valid in an average sense. It doesn't go through the response quantities. So we use another numerical evaluation we use. Innovation is Kriging approach, and you can see it can go through the process, but the Kriging approach through the response, all the black dot. That Kriging was developed for application of in the gold mine, and it is not developed for structural reliability evaluation. We have to use weight factor. It is mathematically very complicated, but I'll give you a reference. We can calculate that response factor explicitly, and then we can use that Kriging method with other sampling scheme to develop the REDSET method we proposed. Now, we cannot go too much in detail, but what we did, then we want to verify the REDSET method. We took a relatively simple small frame, and we excited by a earthquake time history recorded in the past, and we calculate the risk of failure of most of the structural member. It is not readable. So what I did, I'm going to amplify them. And you can see here that when I use Monte Carlo simulation, we are using about 500,000 simulation cycles. But using REDSET, we are using only 100 or 120 deterministic analysis to extract the reliability information. Now, after that, and before we move forward, it took us about 1,000 hours to verify that program. So you may say, how did I get that? One weekend on campus, we integrated as many computer available to us, and we got the result. After the successful verification, then we took a case study. A building in the Southern California suffered tremendous amount of damage during the Northridge earthquakes of 1994. NSF provided a lot of funding to investigate that building, and they identify which member failed and which member did not fail, which member suffered minor damage, and which many different things. We took that and we collected or took the earthquake time history recorded closest to the building, excited that, and then we found out some of the member which failed, the probability of failure is of the order of say 50% or 30%. We are looking for about 10 to the power minus 4 or 10 to the power minus 5. Now, to show the capabilities of this REDSET, we estimated reliabilities of most of the building in the frame. We identify highly damaged, intermediate damage, and no damage area. And that is the very unique feature of our method, really. Okay. Now, as I said before, we need to use multiple time histories to consider uncertainty in the excitation. For earthquake, we have ASC standard. They suggest either use 7 or 11. Yeah, we use 11, and we showed different earthquake time histories. We can do it. And if we use those 11 different time histories, they are going to give you the different probability of failure for each case. Your task could be try to reduce that width of the band as much as possible. And believe me, by changing one member, properties of one member, you can meet that objective. For the wave loading, we are going to use that load on this particular structure. We got the probability of failure, and it Monte Carlo simulation match very well. Here you'll find that the green is for lateral deflection. Offshore structures are very strong about lateral deflection. Blue area is members in the splash zone area, and that splash zone means it is probability of failure is much higher, beta value is lower, and the orange line is the probability of failure for member from away from the splash zone. Then we took that solder ball, and you'll find we represented it by finite element. You can see the dimension has changed significantly. It is in millimeter. Now we consider uncertainty in the time history. We talked about it. I'll give a reference later. And we presented the probability of failure. The solder ball we used, it was tested experimentally. It failed at 3200, and you can see the probability of failure is 90%. There is no mathematical basis for it. Here, material nonlinearity is the basic problem of failure. We submitted a paper in Electronic Packaging Journal, and the reviewer thought our work was groundbreaking. So what we did here, in this briefly, I talked about that we found an alternative for classical random vibration and simulation approach. We developed change the paradigm shift. Instead of conducting one deterministic analysis, a design can be made more dynamic, load tolerant, resilient, and sustainable with the help of few additional deterministic analysis. Now, I told you that I'm going to give you the references. The two books I talked about it is now widely available. It is published by Wiley. This book I'm showing on the left-hand side, it is right now, it is available in March 2023 in this country, in the US. In the outside US, it would be available another 5 weeks or 6 weeks. And here you can see I talked all the discussion I made here, I mentioned in that particular book. So if you want to know more about it, you need to buy the book. Here, thank you. here I'm showing our campus. So thank you for listening to me, and I hope you follow by the book and figure it out what needs to be done, or if you want to know more about the topic. So please buy the book, and that